All right. Many of you know me. I'm a physicist, but I haven't been doing physics for the last decade. So, manager. I'm going to talk about the quantum ecosystem. I'm going to talk a little bit about what's happening that's driving the technology, the money piece of it, and come back to some of the benefits and risks of what's going on, because in some ways this is driving some of the politics around this and the issues of export control and everything else. And so, I'm going to tell you a kind of a complex story. For those of you who don't know, I retired from this and set up my consulting company about 2 years ago. It's been great. I no longer have to deal with all those problems that arise that managers deal with. So QIS, in some ways this is remarkable. I mean, it touches on everything from sensing and metrology to communications, simulations, computing, and I think a lot of robust intellectual connections in between. So to me, this is a really thriving field, and being quantum 2.0, coherence, superposition, entanglement, all these words you've heard. What is my perspective on the overall field? And this is kind of my perspective. There's what we know. You can do quantum measurements today. You can do quantum key distribution or point-to-point quantum communication today. You can go buy those things. I'm not sure they're very practical. The quantum sensors are coming. The problem with quantum sensors is largely the fact that you have to displace existing sensors that are pretty damn good, and you need to do it in a cost-effective manner, which makes this horribly difficult from an economic perspective, because we're just not there. And then we read about everything that's going to come. In the old days, I would put quantum computing out there. My y-axis difficult complexity is some multiplication of the number of qubits and the number of operations you need to do. The longer the operation, the more difficult. Okay, quantum networks may not be that complicated, but they aren't going to become long distance and interconnected until the devices are cheap and I don't need a dilution refrigerator every 50 kilometers. Just not going to happen. So it's way out there. I think people, the first quantum networks will probably be used within a room to connect components of that quantum computer. But there's probably a lot of other things, and some of this has been touched upon. I like the relativistic geodesy, earthquake prediction, other things. Again, it's quantum sensor network. I think that is something that actually has social value. As I've told many people, if you can put a quantum processor and a network into this phone, I can create correlated entanglement and create quantum games that won't play the same way twice because of the way the collapse occurs as the players play out. So this is a multi-billion-dollar market when and if you can get the technology here. I don't know whether it can be done. So what does everybody say? If you go out and look, and this comes from a McKinsey report, but you can look at the Boston Consulting Group, you can look at any of these reports. They all use slightly different economic models, and I'll talk about a couple of them. But effectively, where they come back is the largest market is going to be quantum computing. And in some ways, it's not surprising. They also show numbers up there for quantum networks and quantum communication. But whatever the model is, they all end up in about the same place. I looked at this several times over the past few years. And, okay, there may be a factor 2 difference between the two different reports. Factor 2 is a couple of years, who cares? It's in the noise. I mean, so do I believe any of them? They're all probably overly optimistic. If you look at the investment, and this is interesting, and most of the investment is going into quantum computing, into hardware and into software. This comes from the Quantum Insider platform. You can see what the major ones are. The interesting thing is in 2021 and 2022, there was about $2 billion per year that went in. This year, it looks like it's going to come out around 1.2 or 1.3. A couple of things have happened. Again, economy isn't quite as good. And then there's this so-called thing, ChatGPT, you might have heard about. And believe me, there's some investments going on there that are just sucking a lot of money out of the system. So you can go look at those and see where the money is going and what's going on. I think what most people don't realize is that probably the kind of time frame when everything changed is around 2013 and 2014. At that point, the investments first started with Rigetti. Again, Microsoft had long had a program, but it went into hardware in 2011, Google 2013, but several hardware companies, IonQ and others, came around at that time. And in fact, if you look at the number of companies being created, that has already peaked. So there is more money going in higher, longer rounds, Series A, B, so forth and so on. But the number of new startups has more or less peaked in the system. You can look at where the investments are being made and how they're being driven. And while a lot of the investments are being made in the United States and a lot of the companies are being started there, not all the capital is coming from the US. In fact, in recent years, there's much more venture capital in Europe. And in fact, well, in the two most recent evaluations was another $100 million that went into Oxford Quantum Circuits. That was done by the Japanese, and Oxford Quantum Circuits, of course, in the UK, and another $100 million led by Microsoft that went into the company Photonics, which is a silicon quantum computing company in Vancouver, British Columbia. You know, you can look around where it is, and you know, there's nice sources. Don't trust all the numbers in there. You know, the $15 billion number that everybody quotes for China is basically based on one statement that was told, that has been more or less confirmed several times, be, well, yeah, except that they had the wrong currency. But you know, who cares? It repeats over and over again, and a few other things. But there is money being invested around the world. I think what's more interesting is you can talk about how much money is being invested, whether it's by governments or in venture. You know, the U.S. may have one of the largest amounts of money, but if you compare per capita, Canada is 1/10 the size of us, 1/10 of our economy, and yet they invest 3 times per capita what is invested in the U.S. Netherlands made very big investments. Again, Singapore has. So, you know, there's a lot of things that when you look at these numbers that you can just come back in, and if you sit back and analyze a little, it's not so black and white that everything is on. But there is a global race going on to see who's going to own the technology. I would say, in my view, on owning the technology, no one nation is going to own the technology. In fact, if you look, it's going to be most companies, even the startups, are already starting second offices in other countries and everything else. This is going to be an international game. It's not going to be where one nation owns most of the technology. What's the state of the art? Well, I think if you go and look at what you can get on the cloud that is arbitrary, programmable, accessible, it's currently IBM. Again, the cold atom people, you can see tens of thousands of thousands or tens of thousands of qubits, but they're not arbitrarily controllable. They're still noisy, but there have been at least 3 experiments in the past year showing the first steps toward quantum error correction and fault-tolerant computation. So progress is being made. And multiple companies have roadmaps to 1,000 plus qubits and devices by mid or late 2020s. So I think it's interesting to watch those roadmaps and see how many companies stay on their roadmap. And there are a number that are staying more or less on their roadmap, maybe a little slippage, but everybody expects some slippage. I like this graph that I'll spend a little time on from the Microsoft team, because it talks about what we know versus what we speculate about. And again, there's been a lot of talk about speculation. Most of the people talking about the applications in finance, if you are having to take your classical database and put it into quantum, you need this thing called quantum RAM. It doesn't exist. It's a dream still, as far as I can tell. Okay, a few papers out there that talked about it, but it's basically a dream. So, you know, if somebody's having hallucinating a little bit, it's going to happen tomorrow, the same way that QRAM exists. we talked about the quantum dynamics today, and you know this was interesting. I think this is largely an area for physicists. I've looked to see whether there are any commercial applications out of this. I think finding a commercial application in the area of those green squares, and there's two of them there. Basically, what those squares do is each of those squares basically takes a surface code, an underlying error rate, I believe, of 10 to the minus 3, and then you're just looking at the speed of the computer as you go across on the resources. But quantum dynamics, if you come back to these so-called reduced key factories, you can basically, at a slight cost of time, reduce the overall number of physical qubits you need. The interesting thing is that the blue square with factoring, this is sure, this is going to come, it looks like, before most really sophisticated quantum chemistry things. There's some quantum chemistry that may come before that, but there are a lot of things that you can approximate well already classically and not going to have significant impact. You can ask, okay, what are the modalities? Where are the investments? Well, you can see the superconducting when trapped ions are there. This hasn't been updated recently. There are a couple new ones, but I mean, basically the trend still is there. Photonic has grown quite a bit. NV centers and color centers are something that may come later. And of course, there are a few doing topological, the hypothetical qubit that may exist someday in the future. I want to make a few comments on qubit modality. You know, superconducting qubits are the most common, followed by ionic and photonic qubits. The photonic qubits remain somewhat of a dark horse. But you know, one of the interesting things is if you look at some of the technology that they're developing, they can fail and still be worth $100 billion because they will create the switches, if they fail in the right way, for the all-optical internet. We waste a tremendous amount of energy in all those switching stations. Every time you're running your Google, Netflix, or whatever, you're just burning up bits in those stations as we switch to the internet. Spin qubits, you know, I think they're a dark horse that really is something we have to watch. Why? Well, you basically have a $100 billion industry behind them. TSMC is spoke already today. And you know, the reality is if they figure out how to solve one or two key problems, a lot of their engineering challenges are already done. So you know, they can make a breakthrough, and this can come very rapidly, but they're probably the only one where that breakthrough is likely. And there are a couple more comments on there. A little more about the modalities in the quantum sectors. You know, when you go back to a couple slides to this things, the slower qubits tend to be the atoms and the ions. And again, this was a comment was made about the factor of 10,000 or stuff. Okay, so some tricks. One of the biggest roadblocks on the atoms and ions is the measurement side of it, because you have to scatter photons, roughly 10 nanoseconds. You multiply it out by the 100 or 1,000. If you can create better collection efficiencies, you can significantly do it. Changing the gate speeds isn't currently going to change how fast they can run. You're really going to have to solve the collection problem if you're going to speed them up. Having said this, I don't see my sensors out in the real world being built based on superconducting technology, nor on silicon and spins. Just dilution refrigerators everywhere, it just kind of boggles my mind. So, you know, whatever you say about it, you know, governments need to continue to invest in all of these, because where they will get used and what they will get used for can be quite different. So, you know, I think in conclusion, you really have to continue the race and see where they're useful and what they're useful for. And, you know, again, ions, if I want to build a quantum repeater and need a small quantum processor every 50 miles along my quantum internet, I think I'm going to go with ions at the moment. I'm not going to go, maybe I can do it with photons, but I'm not going to go do this with dilution refrigerators. You know, there are places where this technology is already going. There are several companies now trying to get FDA approval for these magnetic sensors that are being used to replace magnetoencephalography systems. And they were actually quite remarkable. And part of the benefit is that you can go to extraordinarily low fields, which means, and you don't need to have shielding and everything else. So it means that one day in the future, whether on a football field or out in a war field where you want to look at concussions and everything else, you may actually be able to do this in the future. So, you know, again, a promise. And I want to talk about some of the promises. I also talk about the negativity. Having said this, a lot of this talk is based upon a paper, and a few other authors may appear on this paper that will come out hopefully on the archive in the next month or so. It's getting close to being done with just finishing up some things, about over 300 references. Now I think approaching 400 references, talking about what really is going to happen with quantum computers and when are they going to be provenly economically viable. And I just go back to this things. A lot of progress is being made, but you know, you don't get full of money unless you can find economic progress. And so you have to come up with techniques for error correction and other things. And I'm just going to put up this plot because what's on this plot is really the key to understanding what's going on. Basically, when you look, take the depth of the circuit and the number of qubits you need, the width, and you multiply them out, you basically come back and ask, what can I do? And what you find is, I can break codes. That is what is known. And moreover, you know, if you want to read an interesting paper, I encourage you to read this paper by in 2016 by Neil Kobolitz and all, because it talks about what happened on the cryptography side in the past decade. And all I would tell you is they proposed 4 reasons for all the changes that were being proposed by the National Security Administration. I think the answer is clearly number 4, why. This is a plot, and I'm plotting both the elliptic curve cryptography and RSA on a curve. And the RSA is really plotted only against the bits of security on the top. Going from elliptic curve size to bits of security divide by 2, an easy division. Going from RSA back to bits of security, you have to understand the complexity of the general number field sieve, and you can plot that out. What you find is that elliptic curves will be broken first. They're just going to go first. They were used by our governments basically protect information, and it's all of them, NATO, everybody, basically because you could go to longer key sizes and have extra protection. Well, that was classically true. The problem is the quantum computer is going to be far more easy to break. And again, there are several people who have pointed out there may be tricks to bring down the RSA numbers. I'm not going to mention anything more on that. So with that, I'm more or less back to where we started. You know, I think the progress is going very, very well, but one of the things we need is we need better hardware. And we need better hardware largely because in order to find approximate solutions that can work and that you can provably prove work, you need better hardware. I think it will happen. I think there's been a lot of progress made, but nothing that you can prove with existing hardware. And people do toy problems, but the scaling and the coefficients all create all kinds of questions of whether they truly are going to happen. I think there's a lot of evidence that it will eventually happen. But at the moment, one of the first things that will happen will break it. So with that, I want to come back to just a few conclusions. And, you know, a lot of money is being invested. We need to continue this. I think the long term, this will be very, very beneficial. But as a whole, as a group, we have a responsibility to encourage everybody as we standardize the replacement for public key infrastructure, the post-quantum crypto algorithms. They should be standardized soon. We have a responsibility to replace all of our public key infrastructure because we need to remove the risk that this technology creates to our economy and to our nation. So with that, thank you very much.